Good morning, one and all. Today, I would like to explain one more topic on microprocessors and microcontrollers.
This conference will now be recorded. This conference will now be recorded.
Good morning, one and all. Today, I would like to explain one more topic of x86 microprocessor. That is instruction set or types of instructions. Because in the last presentation, we have seen what are the assembly directives, what are the types of assembly directives, and what are the procedures and macros we have seen. Today we will see instruction set of 8086 microprocessor. These are the six types of instruction formats. So one instruction can be written in six types. That's why it is called as six types of instruction formats. Right here we are having 1 byte instruction, register to register, register to memory or memory to register, with displacement, without displacement we have seen. And that address, this is the structure of the program, and that address of way of writing the program is called as addressing mode. The way of, because one instruction may have two fields, one is called opcode field, another one is called operand field. So the way of locating these operands is called as addressing modes. So these are all different types of addressing modes: register based, immediate data based, direct address mode, register indirect address mode, based relative address mode, indexed addressing mode, and based indexed relative address mode. These are all called different addressing modes that we have seen in the previous presentations also. And this is the instruction format: opcode and operands. So opcode means it identifies the action to be taken, and operands means it identifies the data to be operated. That's why we are having mainly two fields, but it may have two more fields also. On left side one field and right side one field. Left side field is called as label field, and right side field is called as comment field. So they are optional fields, but mainly instruction will have mainly these two fields. So this BX register, here copy the content of BX register with the AX register. So that's what is called as, this statement is called as moving or operation. Next, ADD, AX comma BX means add the content of BX with AX register. So it is performing, it's not moving. Why? Because here this ADD performs one operation. So that's why this code or instruction is called as opcode. Now we are going to see this type of opcodes, how many ways we can write and what are different types of opcodes we are having. Okay, so 8086 is having different types of instructions: data transfer instructions, arithmetic instructions, bit manipulation instructions, string instructions, program execution transfer instructions, washer control instructions, iteration control instructions, and interrupt instructions. These are all different types of instructions in 8086 programming. So, for example, you take data transfer instructions. Under data transfer instructions, again we are having four types of instructions. Okay, so under this four types of instructions, first one is called instruction to transfer a word or a byte. How to transfer data from one location to another location, one register to another register, one memory to one register. Like that, we're having data transfer instructions. This right. So these are the data transfer instructions: move, MOV. are PUSH, POP, PUSHA, POPA, XCHG, and XLAT. These are the data transfer instructions under data transfer instructions of instruction transferring of the word or data. Suppose here MOV used to copy the byte or a word from the provided source to the provided destination. For example, here is the move instruction. Move is used to copy the byte or word from the source to the provided destination. So this is the syntax of move. Move destination comma source. Right, so this is the syntax of this move statement and move x comma bx. So here this is called as the statement or instruction or opcode or mnemonic, and these are called as the operands. These operands are always so two types: destination operand and source operand. So source operand usually called as input operand, and destination is operand is also called as output to store the data. Right, but before execution these two acts like a input, and after the execution this place is used to store the operated or the stored outputs. So that's why here we are having this. So the destination can be what type of data or memory or something I can take at the place of destination. So the destination can be a register or it can be a memory location. But source can be a register, source can be a memory location, or the source can be immediate number. So this source, that's why I told you the source operand may be a data value or maybe a register or maybe a memory location. That's why I told you source means input and destination means output. So to before execution, these two can be act as input. That's why here you can see the similar. It may be register, it may be memory. It can be register, it can be a memory, but it can also be a immediate number. And one more thing we have to remember, very important for the interview purpose, is the source and destination cannot both be memory locations at a time. Okay, so this is very important. We have to remember. See, for example, here I am giving move cx comma 037ah. Put 037ah into cx register. So this is what we call the immediate number, right? So move bl comma 437ah. This is what we call the memory, right? The content of the data stored in the address location of 437ah is copied into bl. Antegani 437ah will not be copied into bl register. And now here you see that one more example, move ax comma bx. So here bx and ax both are registers. Here data is from register to register. The content of bx register stored and are copied into ax register. Right. So this is called as the register to register. This is called as memory to register, and this is called an immediate number to register. That's why this part is called a source operand part, and this part is called as the destination operand part. So destination operand may be a memory. You can see here move result of BP comma X. So here BP is having bracket meant memory. So destination memory, when the destination source cannot be memory locations at a time. So if it is memory, next destination becomes register. If source is having memory, destination must be a register. So exchange, this is also very important. So the move instruction always moves or copy the content of source to destination, but destination cannot copy it into source. But here we are having one instruction called XCHC. XCHC stands for exchange the content of the source to destination and destination to source. At a time, source can be copied into destination and destination can be copied into source location. So that's why it is called as exchange instruction. So this is also sometimes used in our programming, right, to exchange the content of source destination and destination to source. Whereas in the case of 8051, we are having three types of instructions: XC, HG, XC, HD, right, XCH. Like that, we are having 2 to 3 types of instructions in 8051 that we will see later. And swap also there to swap the contents of only AX register, and data transfer instructions under input. So we are using in and out. These are the two instructions to copy the input devices and output devices to CPU and memory, or memory to CPU, or sorry, input devices to memory and memory to input devices. We are using this in and out, that we will see later. Next important instructions are instructions to transfer the address. And there are three ways, right? Load effective address, load from data segment, load from extra segments. Then we are having LEA, LDS, and LES. These are the three instructions to copy the data from the, or to transfer data from the addresses. Next, instructions to transfer from the flag registers. LAHF, SAHF. LAHF stands for used to load AH value with the low byte of the F flag register. What is AH value? AH is the higher byte of AX register or accumulator. Please load that accumulator higher byte with lower byte of flag register. What is SAHF? Store AH register to lower byte of flag register. The content of AH register will be stored into the flag register lower byte. Right. Push F. Push the or copy the flag register at the top of the stack. Pop F. Right. Copy a word at the top of the stack to the flag register. These are the two instructions related to stack. LEA, right? For example, I am giving how to use the LEA. This instruction determines the offset of the variable or memory location named as the source and put this offset in the indicated 16-bit register. Right. So, for example, you see here I am giving that. So LEA R2 comma memory, right? LEA R16 comma memory. So whatever the content of this memory is copied into this R32 or R16 registers. Calculate and load the effective address of a memory operand, that is known as LEA. LEA instruction computes the effective address at runtime and used with indirect operands, and effective address is known at runtime only. So this is also one of the very important instruction which will be used in the programming. So that is what we call LEA. So this LEA is also having register and so suppose say for example LEA BX comma prices. Load BX with offset of prices in data segment. Data in the data segment, we are having the prices name variable, and that will store different prices of the components, and that every component address is loaded into the BX register one by one. That is what we call LEA. Next one is arithmetic instructions, and these instructions are used to perform arithmetic operations. Used to perform arithmetic operations like addition, subtraction, multiplication, division, and so on. Right. Following are the example of these arithmetic operations. As we know that arithmetic means addition, subtraction, multiplication, and division. So here you see, right, the instruction to perform addition. What are different types of instructions we're having to perform addition are ADD, ADC, INC, AAA, and DAA. Right, what is ADD? Add or addition. ADC, add with the carry. Suppose if I want to add three values, then first I will add the first two values, and when we add first two values, it generates sum and carry, and this carry is again going to add with the third element, and that will generate the final value, which is known as the add with carry. If in the case of subtraction, we use subtraction with bar, right? ENC, increment means it is also addition of addition by 1, right? Use it to increment the provided byte or reward by 1, right? Use it to adjust ASCII after addition, right? The values which you got will be adjusted to ASCII format, right, after the addition. Next, DAA, use it to adjust the decimal after the addition or subtraction operation. Next, subtraction, right? Subtraction, use it to subtract the byte from a byte or word from word. Subtract with bar. Decrement means it is subtracting the by 1. Next, CMP means use it to compare two byte provided by word or a byte. Comparison means again subtraction of two values only. Okay. So for example, here I am giving syntax of addition. So ADD destination comma source, ADC destination comma source. So here this is the syntax. So these instructions add a number from some source to a number in some destination and put the result in the specified destination. Right. So here the source may be again immediate number, a register or a memory location. Here the destination may be a register or a memory location, like same like your move statement. Here the flags are affected by auxiliary flag, carry flag, overflow flag, sign flag, and zero flag. These are the flags will get affected in the flag register. Suppose see here I am giving one example, right? So this one and this one are the two input values, 11010010, 11110101. These are the 8-bit values. When I am adding always it is generating carry. See 11, right? Some 0 carry 1. You know that 11 some 0 carry 1. Like that if you add, at the end we are having three ones. When we have three ones, sum is 1 and carry is also 1. If you have doubt, you can go through the full adder. Then the sum, the final carry, the final value is called as carry. Because when I have the 8-bit addition, I got 9 numbers. You see 1, 2, 3, 4, 5, 6, 7, 8, and 9. So what is the name of this ninth bit? It is called as carry. So where this carry will be stored? This carry will be stored in the flag register of 8086. Let's see here. So here CY is called as the carry to indicate that the final bit of the addition or subtraction. Here subtraction also bar also indicated by this carry only. Right. And instructions, arithmetic instructions used to perform multiplication. Why I'm explaining here multiplication and division is multiplication and division are having the separate syntax. That's why I want to explain here multiplication and division. So multiplication of unsigned numbers is MUL. Multiplication of signed numbers is IML. Multiplication of ASCII adjustment is AAM. Right, multiplication of division of unsigned numbers is div. Division of two signed numbers is IDIV. ASCII adjust after division is AAD, and sign bit for sign bit they are using CVW and CDW for word and double word. See multiplication, and so this is the syntax of multiplication. Right, mul source. That's all. It does not have any destination. Why? Because we know that internally multiplication will take so many steps. So to avoid that, what they are doing, they are taking only source operand here. Okay, this instruction multiplies an unsigned byte in some source with an unsigned byte in AL register. So here, if the multiplication is between byte to byte, then it will take by default the content of AL and the source value. Okay, next, if an unsigned word in some source with an unsigned word with AX register. Suppose if it is word to word multiplication, means 16-bit multiplication, then it will take the source. The source also must be 16-bit, and by default it would take the content of AX to multiply the two numbers. Right. So then when it is multiplying the AL with source byte, then the content again is stored in AX register, because 8 bits 8-bit multiplication will give 16 bits, because 2 power 8 into 2 power 8 is equal to 2 power 16. So to store that 16-bit result, we need AX register. Next, when a word is multiplied by the content of AX, the result is put in DX and AX registers. Means you want to multiply 16-bit, then 2 power 16 into 2 power 16 is equal to 32. So to store the 32, right, destination here AX register is not sufficient. Then it is taken the help of DX register. DX stands for data register. The main purpose of DX register is used in multiplication and division operations. Next, if you want to multiply byte with a word, right? Suppose you want to multiply byte with word means 8 bits with 16 bits. In your 8 bit and remaining 8 bits must be filled with all 8 zeros. Then it becomes 16 and 16. Then you can multiply. So these are all example of multiplication, and this is the division, same as the multiplication. Here we are having div source. It does not have two operands. It is having only one operand. This is called one operand program instructions, right? And this instruction is used to divide an unsigned word by a byte, or to divide an unsigned double word, or by a word. It can be divided by 16 bits, it can be divided by 32 bits, and it can be divided by 8 bits, 8 bits. Then if you are dividing byte by byte, or if you are dividing 16 by 16, if you are dividing 32 by 16, then remainder and coefficient will be generated. Remainder will be stored in AX register or AL registers, and the coefficients will be stored in AX register and DX registers. If it is a double word by word or word by word, then the remainder and coefficients will be stored by DX and AX register. Whereas it is byte by byte, and remainders and coefficients are stored by this AX register, because AX is having both AL and AH. You see here, AL will be contain the 8-bit coefficient, and AH will be contain the 8-bit remainder. So 8-bit means 16-bit, and this 16-bit content can be stored by this AX register, whereas AX is a 16-bit register. Right. Suppose if you are dividing any number by 0, then you know that according to mathematics, if it is 1 by 0 or something by 0 is called infinite, then that will be identified as interrupt. It's called type 0 interrupt. So the 8086 will automatically do a type 0 interrupt if the result of a division operation is too large, which will not fit in the destination register. Right. Sometimes it is over the destination register of more than 16 bit, then this division operation will be go to the type 0 interrupt, and then it will give the output as the so and so will give the to having too much or too large output. That is what we call the divided by 0 output. Okay, next one. Increment. Increment is also having only one operand, but here it is having destination. Where in the case of division and multiplication, we are having only source, but here we are having destination. Destination means what, after performance of operations, what needs to be incremented. So that is what we call the destination. So it always incremented by 1 byte or 1 word only. This means that 8 this instruction adds 1 to the specified register. Either if it is BL, AL, then 1 byte. If it is AX, BX, 2 bytes or 16 bits. Right, next, DSA. DS means decremented by 1 byte. Destination word array byte. You see here the instruction subtracts 1 from the destination word array byte. Always decremented by 1. It is 5, 4, 3, 2, 1 like that. Okay. So DIA is also very important. This instruction is used to make sure the result of adding two packed numbers is adjusted to be legal BCD number. Right. The result of the addition must be in AL for DIA to work correctly. Right. Result will be stored in AL or AX register to know the exact value. Sometimes if you don't have much knowledge on BCD numbers, and after adding up to subtraction, if you put DIA or DIS or DIM or DIAD, then that will be adjusted to the known BCD number. Next, AND. AND means here these instructions are called as the logical instructions, and here the logical operations are AND operation, OR operation, NOT operation, XOR operation. So here, for example, I am giving the AND operation. Here it is having two operands again, and destination comma source. This instruction adds each bit in a source byte or word with the same numbered bit in a destination byte or word. The result is put in the specified destination. Okay, so here the result is performed AND operation between destination and source. To perform to AND operation, here it is performing bit by bit operation only. That's why here is having once again destination and source. But in the case of division and multiplication, lot of steps are required. That's why it is having only source. And bit manipulation instructions are two types: logical and shift operations. Logical already we have seen. Along with that, we are having NOT gate, OR gate, XOR gate, and XOR test one. And the test also performs the AND operation, but it will not affect the any operands. Right. See here, test destination comma source. This instruction also performs the AND operation between byte or word in the specified source with byte or word in the destination. And flags are updated, but neither operand is changed. No operand will be changed. The operand contents will be as it is. Okay, but flags will get affected. Right. Not operation. Not operation means only one input, so not destination. This act like a source and destination. It performs they not bx means the content of bx will get complemented. Next, in the bit manipulation instructions, we are having two types: shift and rotate instructions. The shift and rotate instructions. What are shift and rotate instructions? Here there are two types of instructions. One is called circular shift. Another one is called as bit by bit, either left side or right side. If it is right side and left side bit by bit instructions, rotation is called as shifting. Right. If it is complete circular shift, either towards right side or towards left side, is called as rotation. That is the difference between shift and rotate. So here when you are shifting, we are having SHL or SAL, shift left arithmetically and logically, right? Shift right logically, shift right arithmetically, right? Rotate right and rotate left with and without carry, ROL, ROR, RCR, and RCL. Here C stands for with carry, and here without carry. That we will see with the example. Right. Suppose I am having RCR, right? Shift right. S stands for shift, R stands for right. With arithmetically. What is arithmetical shift? We will see. Right. This instruction shifts each bit in the specified destination some number of bit positions to the right side. As a bit is shifted out of the MSB position, a copy of the old MSB is put in the MSB position. Right. Suppose you are shifting here 100. This one is shifted towards right side, and it will next this position is empty, but again it is filled by the previous MS bit of 1 again, means then it becomes 110. Instead of 100, it becomes 1110. So that is what we call the SAR, destination comma count. Right. Next, what is SAL or SHL? Is nothing but here these to perform same operation. Here you see, right, when you are performing left logically, then what is happening? Left side means this side. Then what is happening? Right, left. This is called as LSP and this is called MSP. Right, the LSP bit is filled with 0 here. Right? This instruction shifts each bit in the specified destination some number of bit position to the left. As a bit is shifted out of the LSB operation, a 0 is put in the LSB bit. So here I have to put the 0. Okay, but whereas in the case of SCR, here this MSB shifting right side, the previous MSB will be shifted here and placed here. And R rotate right without carry. Right. You see here, right side means this one. So this is the MSB and this is the LSB, and carry will not be changed. Right. So here MSB bit is shifted to LSB and LMSB is shifted by one bit, and here it will get adjusted. So this instruction rotates all the bits in a specified word or byte some number of bit position to the right side. So the operation is designed as a rotate rather than shifting, because the bit moved out of the LSB is rotated around into the MSB only, not with the carry. So the data bit moved out of the LSB is also copied into CF. The data bit moved out of, so from out of this LSB can be moved into carry. Right. In the case of multiple bit rotate, CF will contain a copy of the bit most recently moved out of the LSB. If number of times repeated, repeatedly rotated, the recently rotated bit of the LSB only can be copied into CF, that is carry flag. Next, SCR. Right, SCR means shift right automatically. So here you can see that string operations. String operations means, right, when you want to copy a string of characters to some other location, you want to compare two strings, you want to find some word in the given sentence, then that is what we call string instructions. And these string instructions are using repeat based instructions, moving of string operations, just comparison of string, right, loading of the string and scanning of the string, and input and output based instructions also can have the string instructions. Right. So for example, here see REP instruction used to repeat this given instruction until counter is 0. So how many times it must be repeated the same operation is nothing but there must be some value. So that value stored in CX register. Why only CX register? Because CX is called as the counter register. Okay. And REP and REPZ. REP and REP repeat if equal and repeat if 0. What is that? Right. If CX value is 0 is nothing but repeat if 0. Right, repeat if equal. If both are equal means the subtraction takes place and the value is 0. So then 0 flag will be 1. If repeat if not equal, the content of CX is not equal to 0, then repeat and repeat. Right. So here compare. Compare used to compare two string bytes. Use it to scan the string byte. I want to pick up one word. I want to pick up one letter. Then I have to scan each letter on the given string. That is what you call scanning and loading of instructions. Next, program execution transfer control instructions. These are also called as branch and loop instructions. And these instructions are used to transfer or branch the instructions during an execution. And these are two types, conditional branch and unconditional branch. So during unconditional branch, here we use call statement, RET statement and JMP statement, right? During conditional statement, we use condition, we verify the status of flag register, and then it will verify this, it will execute that instruction. So for example, and we will see later. Right. So in this program execution transfer instructions, how JMP instruction, this is called a JMP instruction, use it to jump to the provided address to proceed to the next instruction. So how it will jump to the specified address locations. Here you see there are three types of jump: near jump, short jump, and far jump. Right, near jump. We know that when some instructions are executing, right, then sometimes the loop needs to be repeated, then we have to jump to the data location either upward or downward. So then it is within the segment or outside of the segment. That means code segment, data segment, or data segment, code segment are within the code segment itself is known as the near jump, short jump, and far jump. If near jump means a jump to an instruction within the current code segment, right? Within the current code segment, sometimes referred to as an intra-segment jump also. I told in the addressing modes, right? And short jump, a near jump where the jump range is limited to -120 into +120. If it is 8-bit jump, if 256 locations, that is called a short jump, right? Far jump, right? Anywhere in the program with greater than 8-bit up to 16-bit is known as far jump. Okay, there are three types of jump in the programming. Okay, the jump instruction fetches the next instruction from addresses at label continue. JMP continue means continue somewhere has written with the label, and that will be go to that location if the JMP instruction has written without check any condition. Next, call and RET. So the call instruction is used to transfer execution to a subprogram or a procedure. I was explained this in the procedures and macros. These are all called out. Whenever you want to call the subprograms, right, then we will use this call statement. And there are two basic types of calls: near call and far call in 8086. Right, far call means anywhere you can jump, and a near call means is a procedure which is in the same code segment. Right, a for call is a call of the processor which is in the different segments, then it is called as for call, and this call statement is always terminated by using this RET statement. Next, program execution by using condition. What is the condition? If by comparing two strings, by adding two strings or two values, if we add two values, then what happens? Carry may generated, auxiliary carry may generated. If you subtract two numbers, then sign bit may generated. Right, and like that, you can have the different types of condition checking. Right, overflow may occur. Next, parity may generated, greater than, less than. These all kind as the conditions. So whenever you want to jump to a specific address location, so first if you want to test that condition whether it is true or not, Then we use all these condition-based program execution, transfer or branch and loop instructions. These are also very, very important for the exam programming point of it. Right. For example, you take JE by JZ. JE by JZ means jump if equal or jump if zero. So this instruction is usually used after a compare instruction. Means comparison always takes place between two values minimum. Right. If these two values are same, right, then it will execute as equal or zero. If they are not same, then it will give the not equal. Right. Then the statement will have to return JN, jump if not equal. So this loop will be continuously executed until they are equal. See, for example, CMP BX and DX, compare BX with DS. Here comparison takes place with the help of internally subtraction process, but these two will get equal, and this condition will satisfy JE, jump if equal. When they are equal, automatically the result is zero. Zero flag will be high. So that's why here they are giving under one. JE by JZ. Next, processor control instructions. So how to control the processor? Right, you can control the processor. And processor will execute arithmetic and logical instructions using execution unit. Then, if you have the carry already, then you can set that carry. If you want to clear that carry, you can write CLs. Use it to clear or reset carry. Right, use it to put complement at the state of the carry flag. STD. Use it to set the direction flag. CLD, use it to clear or reset the direction flag. STI, use it to set the interrupt enable flag. CLI, use it to clear the interrupt enable flag. Right? You want to set or reset the interrupt flag, and you want to set or reset the direction flag. You want to set or reset or complement the carry flag will be done by using this processor control instructions. Next one, iteration control. So like that branch and control instructions, if we want to execute the loop for number of times, then we have loop instruction. These instructions are used to execute the given instructions for number of times. So following is the list of instructions under this group. Whereas the JMP call RET, they are just to process control branch and loop instructions. But here iteration means number of times you want to execute the same instruction. So adding of 10 numbers, comparing of 10 numbers, right, verifying of the string by comparing number of times is known as loop. Loop if equal or loop if zero, loop if not equal and loop if non-zero. JCXZ, jump to specified location until CX value is 0. Use it to jump to the provided address if CX equal to 0 always is known as the iteration control instructions. So these are also very, very important in terms of programming. See, for example, here, right, interrupt instructions. These instructions are used to call interrupt during program execution. Right, INT is the interrupt instruction. After this INT, you can write into 02 into 255 because interrupts are two types: hardware interrupts and software interrupts. Hardware interrupts are caused by the external hardware when you are placed into the CPU, whereas in the case of software interrupts, these are interrupts are internally generated. That's why these software interrupts are represented by using this INT statement or opcode. So that's why here we are having two types of 256 types of interrupts of software, and those 256 interrupts can be represented by using this INT statement from int 0 to int 255. So for example, type 4 or int 4 is also called as the into used to interrupt the program during execution if overflow flag is equal to 1, right? IRET means after executing the interrupts, you want to come out of that interrupt loop by executing these interrupts. Again, you have to go back to the main program, right? Then we use this IRET to return from the interrupts. Then we are having these three instructions. NOP, and at the time of some programs using the statement. This NOP statement is performs no operation. No operation means at that time no operation, but this instruction simply uses up 3 clock cycles and increments the instruction pointer to point to the next instruction. The NOP instruction can be used to increase the delay of a delay loop when coding. A NOP can also be used to hold a place in a program for instruction that will be added later. NOP does not affect any flag. Means here to perform this NOP, it requires 3 clock cycles. After 3 clock cycles, again the instruction pointer point to the next instruction. Okay, within that 3 clock cycles, it does not perform any of. Suppose blinking of an LED is there, then we need some delay. So that delay can be called by using this NOP statement. That is what we call the NOP operation. So thank you. If you have any doubt, please ask me. So these are all different types of instructions.